Alright, welcome to a pretty rare late night video. So this next one is a huge topic. It's neural networks. So sometimes I think what can happen is if you have a big next section, you can keep putting it off and off and off because it's like, oh, this is a big one. I want to be ready for it. And I think that this could easily, if I were not making these videos and I were just reading the book or like, this could easily be where I stop reading the book because it's just too big of a topic to address with anything but the utmost importance and seriousness. So I can't start it today because X, Y, and Z. I can't start tomorrow because of X, Y, and Z. No, that's just a self-defeating way of doing things. So if I can only read one paragraph in this video, that's what I'm going to do. I just want to make sure I'm not constantly putting this off because I'm building it up in my mind as something that needs to be put off. So all right, diving right into it. So neural networks are a relevant topic in the field that I have decided to dedicate an entire chapter to it. There's such a relevant topic in the field that I've decided to dedicate an entire chapter to it. So that's where I'm like, oh, well, I should dedicate, a whole bunch of videos to it. No, just read the book and then decide what to do after that. It probably deserves multiple dedicated books, but let's stick for now to the fundamentals. While I have tried to explain the different algorithms and techniques based on the type of problem they can solve, regression versus classification, in several cases some of these techniques can be used for both, as we have seen. This is also the case for neural networks. Nevertheless, neural networks' scope and possibilities go beyond other techniques, so I think they require a more profound and dedicated explanation. Let me start by saying that neural networks are very sexy, although they're not the preferred solution for the Kaggle problems. The mystery around them, the perception that they replicate the human brain tissue behavior, have led to a particular preference by many in the AI/ML industry to use them because that will make their projects more appealing. Ultimately, as any other algorithms introduced, neural networks are just a tool with pros and cons. It is true, however, that neural networks have such a broad spectrum of applications and potential that they are irresistible for many. I must confess, I feel there is something magical about them in the way and ability to solve certain use cases that look impossible. Let's keep our objectivity and use the right tool for the right problem. In this section, I will explain how they work, their different types, and their applicability. My goal is for you to clearly understand the what, the how, and the why of neural networks. You may have heard or been told that artificial neural networks mimic brain tissue. While the analogy has served to bring attention to them and even help explain its operation, it has been long debunked the parallelism with the biological neural tissue. This reality does not diminish, though, the potential and capability of the artificial. So it does not diminish, though, the potential and capability of the artificial neural networks. I wish this whole though was not there. It simply demystifies the comparison with the human brain cells as a significant oversimplification. Let's explore the basic concepts and motivations behind a neural network. We have seen that for supervised learning, ultimately the goal is to find the function that best approximates the problem we are trying to solve. Very frequently, the relationship between the input variables and the target/label is strongly nonlinear. That means we need mechanisms that can learn and support such non-linearity. We have also seen the general concept that you can achieve great results by combining a set of weak learners, and there could be various methods, stacked in series, parallelized, etc. So you could think there could be a way to build complex models out of a specific simpler model that we combine in different ways. Let's keep that intuition for now. We have also learned the role of the gradient descent mechanism to iteratively approximate a model's weights or parameters towards the global minimum of the cost function. Let's also remember what the loss or error function is. The cost function estimates the combined loss or error for a certain input dataset between the target label and the predicted label. It is the sum, I'm oversimplifying here, of the loss function, where the loss function estimates for a particular observation what the difference is between the predicted value and the actual label value. The goal of any model in a supervised learning scenario is to minimize the cost function. We will see some of these functions in subsequent sections. Let's do a quick recap. We have need to capture nonlinearities, need to capture complex relationships, so a combination of simpler models could be a good approach. Gradient descent as a technique to minimize a cost function. We can generalize more and refer to it as an objective function that you want to optimize, either maximize or, in this case, minimize. Let's remember one technique we described earlier in the book, the logistic regression, which has the following structure. All right, and I guess I might as well put this in to the ChatGPT. I don't know how useful this is, but I'll put it in there anyways. So, yeah.
The image you uploaded illustrates a fundamental concept in neural networks and logistic regression, showing how a linear combination of inputs is transformed through a nonlinear function, specifically a sigmoid function, to produce a probabilistic output. This setup is a basic representation of a neuron in neural networks, particularly as used in binary classification tasks. Here's a detailed breakdown of each part. Components of the diagram. Input X. This represents the input features of the model. In the simplest case, as depicted, there's a single input feature XXX. Bias B0 and weight B1. Bias B0. This is analogous to the intercept in linear regression. It allows the model to adjust the threshold at which the activation function triggers. Weight B1. This modifies the influence of the input XXX on the output. It's similar to the slope in linear regression, determining how changes in XXX affect the output. Summation plus. This operation computes a weighted sum of the inputs plus bias. The formula for this part is B0 plus B1x B underscore O plus B underscore 1x B0 plus B1x. Sigmoid activation function, C, the sigmoid function, represented here as CCC, is a common activation function in neural networks used to introduce nonlinearity. It maps any real valued number into the range 0, 1, making it suitable for binary classification tasks. Mathematically, it's defined as sigma c equals 11 plus e minus c, sigma c equals frac 1, 1 plus e caret c, sigma c equals 1 plus e minus c1, where z is the input to the function. In this case, c equals b0 plus b1x, c equals b underscore O plus b underscore 1x, c equals b0 plus b1x. Output Py. The output Py represents the probability that the dependent variable YYY takes on a particular class, typically one in binary classification. This output can be used directly to make predictions by setting a threshold, commonly 0.5, where values above this threshold predict class 1, and values below predict class 0. Flow and functionality. Linear to nonlinear. Initially, the model computes a linear combination of inputs, which is a linear operation. However, applying the sigmoid function introduces nonlinearity, which is crucial for modeling complex patterns in data that linear models can't. Graph of sigmoid function. The graph included in the diagram shows the characteristic S shape of the sigmoid function. The curve demonstrates how the sigmoid function responds to different values of z's, smoothly transitioning from 0 to 1. This transition zone is where the model is most sensitive to changes in input XXX. Applications. This basic neural model setup is widely used in binary classification tasks, from spam detection to medical diagnosis, where the goal is to predict whether an instance belongs to a particular class based on the input features. This diagram effectively encapsulates how simple neural networks or logistic regression models transform inputs into outputs, bridging linear algebra and nonlinear activation to perform classification.
Okay, so that was actually pretty cool. It actually called out the summation formula that's going to be so the model estimates a p probability value which corresponds there's a typo there to the following formula: p equals sigmoid, and then it actually is the same formula that was called out by ChatGPT. So that's really cool. ChatGPT is pretty smart. All right, so the sigmoid component enables a nonlinear behavior on top of the linear regression component inside it. Due to the sigmoid's shape, it is helpful for nonlinear relationships and predicting a probability value since it varies between 0 and 1. The structure depicted in the picture is also referred to as a perceptron, and I've heard that term before. A perceptron has n input signals, where n is the dimension of the input vector x. There is a residual or intercept value. The perceptron produces an output value which is scalar y. It has n plus 1 weights or parameters b0, b1, and so on, all the way to bn, whichever number, and it's continuous. It is not mandatory to use the sigmoid function. The nonlinear component of the perceptron is referred to as the activation function. The goal of an activation function is to force a nonlinear behavior. And I need a quick break. All right, I'm back and I feel a lot better now. So let's see here. The goal of, reading the book. So the goal of an activation function is to force a nonlinear behavior. But which one to use will be different depending on the use case. It is called activation somehow in analogy with the human neuron behavior, where, based on specific biochemical input in the dendrites, so this is a part of the brain, it will activate eventually an electric signal through the axon terminals, doing a super simplification here. So, so somehow the intuition is that when the input signal reaches a certain level, it activates the response in the axon that will serve as input in the dendrites of neighboring neurons. Following this analogy, our activation function in the perceptron will trigger such activation, a signal out, based on a given combination of input values, of which of course will depend on the weights, B0, B1, and on through Bn. So one thing I really like to do when it comes to human anatomy, stuff like that, is I like to get a good sense of what it means by going to a site called Zygote Body, ZYGOTE, BODY.com. So now you can load in male or female. Let's go with the male just because I'm male. But you can go with either, and then it's going to be the same when it's dealing with things like the brain. So let's see here. So now let's put in some of the terms that we just encountered. So the first term was axon, AXON. So you can go to search here and we can search for an axon. Okay, so axon, we don't get any hits. We've got a hit for auxiliary vein. There's by the shoulders there are that, but we don't have any hits for anything in the brain. So let's look for the other one, which is DENDRITE. All right, and again, there's no hits here, so it's not perfect. It doesn't have everything. It's more you can see here. It's really not. It has some about the brain, but it's not specifically about the brain. So we can look at the brain, but it doesn't have every single aspect of the brain, especially not like that far in the dendrites or whatever. So it has all the structures of the brain. It's very in depth, but it doesn't have the dendrites. Yeah, these are the specific nerve cells themselves, so it doesn't go that deep. Okay, so there are cases where the activation is linear. In this scenario, we will use linear activation, the identity function. So linear activation, y equals function of x equals x. Obviously, this activation function cannot capture nonlinearities. For nonlinear functions, the following four are the most frequently used. So these are for nonlinear functions: sigmoid, which we saw before, then it's the tan h, hyperbolic tangent, then the ReLU, which is nonlinear, but it's a combination of two lines, and then the leaky ReLU, which again is a combination of two linear lines, making it nonlinear. Sigmoid and tan h tend to be computationally expensive, so ReLU and leaky ReLU have become very popular among many neural network and deep learning applications. There are also specific differences relative to how the activation function influences the overall training process of a neural network, but I will not enter those details for now. Nevertheless, let's go back to our thought process. There is a simple component that we call perceptron that can facilitate a nonlinear regression with output values depending on the activation function used. Suppose we want to build a complex model with this atomic component. In that case, we could combine many of these so they contribute to an overall prediction or classification, both in parallel and in series. So let's take a look at this. Oh, and you know what? I don't have it set to my... I'm not wearing my headphones.
The image you uploaded contrasts a single perceptron model with a multi-layer perceptron MLP, illustrating how neural networks can be extended from simple to more complex architectures. Perceptron structure. The left side of your diagram shows a single perceptron, which is the simplest type of neural network. It consists of a single neuron with a single input xxx, a bias b0b_0b0, and a weight b1b_1b1. This setup calculates a linear combination of the input and bias b0 plus b1x
Yeah,
b
so it's
underscore
one
plus b
component
underscore 1x b0
of
plus
this.
b1x, which is then passed through a sigmoid activation function, SysCC, to produce an output YYY. Functionality. The perceptron can make decisions by mapping input data to an output prediction. This type of model is capable of binary classification, but only when the data is linearly separable. Multilayer perceptron MLP structure. On the right side, a multilayer perceptron significantly expands on the idea of a single perceptron by introducing multiple layers. This includes an input layer, one or more hidden layers, and an output layer. Input layer receives the input features x1, x2, xmx underscore 1, x underscore 2, ldas, x underscore mf1, x2, xm. Hidden layers consist of neurons P that each take a combination of inputs from the previous layer, applying weights and biases similar to the single perceptron, followed by a nonlinear activation function. Output layer produces the final prediction output YYY. This layer can consist of one or more neurons, depending on the complexity and requirements of the task, e.g., binary classification, multi-class classification, or regression. Key features and advantages of MLP. Nonlinearity. Each neuron in the hidden layers includes a nonlinear activation function, allowing the network to capture complex patterns and relationships in the data, far beyond what a single perceptron can achieve. Capability. MLPs can approximate virtually any continuous function and solve problems that are not linearly separable, which is a limitation for a single layer perceptron. Training. MLPs are typically trained using backpropagation, an efficient algorithm for adjusting the weights of the neurons in the network based on the error rate of the output compared to the true labels. Applications. MLPs are widely used in a range of applications including speech recognition, image recognition, and machine translation, where complex data patterns must be recognized and categorized. This comparison effectively showcases the evolution from simple linear models to more advanced and capable neural architectures, providing a foundation for understanding how layers and depth in neural networks contribute to their powerful capabilities in handling diverse and complex datasets.
Alright, so moving on, we can build more sophisticated structures from that individual component, the perceptron, to capture more complex nonlinear relationships between the input x, m-dimensional vector, and the output y. Each of the units, perceptrons, will have its own set of weights, b0, also known as bias, and b1 through bm, which we will refer to as w1 through wm as weights. Every perceptron in the hidden layer will have m plus 1 weights that need to be computed during the training process. The input layer is fully connected to the perceptrons on the hidden layer. Likewise, the output of the hidden layer is fed as input to the perceptron on the outer layer. On the output layer. The output layer aggregates the decisions made by the hidden layer and provides the model's final result. This structure, called multi-layer perceptron, is the most basic form of an artificial neural network. So I feel like that's a good place to stop. We got a description of the most basic form. So in the next video, we'll look at more advanced forms. 10 o'clock, and I'm kind of shouting in my apartment complex in my room, so it's probably quiet hours. And then myself, I'm getting tired. I'd like to go to bed. So yeah, that's going to be it for this video. We learned about the most basic form of a artificial neural network, which is a multi-layer perceptron. So stay tuned for the rest of the chapter.